We are often, it's kind of interesting. So when a lot of times when people come up to me and ask me about Kensho, I tell them that we're a startup. By now we're not really anymore, but let me try to give you a little bit of a sort of a historic summary of how Kensho came to be and what we do on a regular basis. So we were founded in about 2013 on the interface of really technology and finance. So our earliest backers were Google Ventures and Goldman Sachs. From there, we ended up doing a lot of kind of interesting machine learning and technological solutions in the finance space. So many of our early backers were various banks, investment banks, hedge funds. And one of our core strengths was really analyzing the large financial universe, looking at events, looking at time series, markets, behaviors of people within markets. And as the time goes on, this universe becomes larger and larger. There's more and more unstructured data, news. Everybody's interest becomes more and more in trying to bring structure to this. And this was something where Kensho early on developed a lot of experience and helped a lot of our partners in bringing some sort of structure to this complexity. We then also ventured out into the national security space, and that was a sort of a very, very natural extension. So In-Q-Tel was one of our backers afterwards. They're the venture capital arm of the CIA. And this was a sort of a logical extension from the financial universe to say we care about events, we care about when, where they happen, what their impact is, and so does the geopolitical universe and government agencies. So that was a clear next extension for us to go into as well. And then most recently, a little less than a year ago, we were acquired by S&P Global. And coming from a machine learning scientist, that's amazing. S&P Global is one of the biggest financial data providers. So being partnered with a company whose business it is to have data is an amazing opportunity. And I don't know, whenever friends ask me how the sort of the transition became, that's pretty much all I can answer. I think most of you guys probably working in machine learning, you know what problems you face whenever you try to acquire new data. Data is very costly. It's usually not of the quality that you really want it. If you partner with somebody, there are all kinds of hoops you have to jump through. You're probably not going to get the full data set. It'll be anonymized. It'll be time trialed. It's always a problem to get enough data or the right kind of data that you're looking for. So, for us, this kind of partnership is kind of an amazing starting out point. Okay, so what will I be talking to you about? I think the main message that I really want to make sure to bring across today is that you have to make sure that you have the right practical approach to whatever problem you're solving. Within Kensho, we've, even within the machine learning specific parts of it, we've been exposed to various different problems across the board. And many of these problems require a deep neural net that's trained for weeks, and many of them require simple, solid, good engineering. So whenever you're faced with a new problem, it's very important to make sure that you understand what are the constraints of it, what are the requirements, what are the tools that you're willing to try out, and how much time are you willing to invest in those. So specifically, I'll try to talk about some of the actual real-world NLP problems that we faced at Kensho, and try to really sort of walk you through what we were thinking and how we were developing these over time. So specifically, I'll talk first about a synonyms model, a way to figure out how we can expand a word to its synonyms, and about record linking, so the task of having two diverse data sets and linking them together. Since this is really supposed to be a sort of a real-world take-home kind of talk, please ask as many questions as you can. This will make for a better talk, and I'll know whether people are on board, whether people think it makes sense what I'm saying. And then at the end, don't leave. We'll have a hands-on workshop. So we will have, like Matt already mentioned, we'll have multiple people in nice blue sweatshirts. There'll be a data set for all of you to download, and to whoever is curious and wants to play around with record linking. We've made a very nice toy data set for people to play around and ask questions and really have a little bit of a hands-on experience about what we just talked about. And we'll be around here for questions for everybody. Okay, so let's dive right in. Let's start thinking about synonyms. Does anybody actually have a computer open with internet? Perfect. can you go to Wikipedia and search for the turtle and the rabbit within the Wikipedia search? It's okay if it takes time. What did you find?
Cecil turtle, rabbit.
I'm not reading. It's still the same. Okay, excellent. I intentionally cut it off after the first search result. Yeah, so you search for the turtle and the rabbit, and you don't get any sensible results. Wikipedia will tell you turtle and the rabbit doesn't exist, and then bring you to various pages about parts of what your input was. Now, if you try the same search on Google and prefix it with Wikipedia, so you go to Google, type in Wikipedia, turtle and the rabbit. I'm going to take it away from you.
I get the tortoise and the hare.
Aha! Yeah, so if you do this now on Google, you literally get the Wikipedia page for the tortoise and the hare. So Google has figured out that not only you're looking for a Wikipedia page, but that you're actually looking for the story of the tortoise and the hare. So if you really think about this, Google did something very clever behind the scenes here, right? That's very non-obvious. It figured out that turtle is tortoise, that rabbit is hare, and even though your input has almost nothing to do with the actual output, it correctly matched it onto what you're probably looking for. But let's take a more finance-specific example and something that within Kensho we actually care about a lot. So one of the products that we're working with a lot is searching within the financial universe. So having people enter any sort of search queries that they're interested in, and then within our data sets, figuring out what the person is interested in. So take the input query, I need companies negatively affected by Obamacare. That sounds like a pretty straightforward sentence. If you give this to an analyst, they would probably pretty quickly come up with some sensible company responses to this. But if you think about what a computer has to do to parse this, it's really not an obvious thing. So you have to understand multiple things about this query. First, you have to understand that companies is an entity. People are interested in companies. This is a request for a list of companies. Companies is something that we have. We have a table in our database that lists various different companies. But now we also want to apply a filter. We want to have them be negatively affected by Obamacare. What does negatively affected mean? What does even Obamacare mean? Obamacare is a very colloquial term where most people will have heard about it in the news. They know, oh, right, this is the PPACA Act, the Patient Protection Affordable Care Act. But it's something that's not obvious just from reading the sentence. But if we can figure out, for example, that Obamacare is really mapping onto the PPACA, which is the more official way that this will be referred to in various company filings or potential news documents, we can then build together a clever pipeline where we look within company filings, where every company talks about its risks, its exposures, its plans for the future, and we can then pick out the risk section, look where people mention PPACA, and then quickly build this into a pipeline where we filter to exactly what the person was requiring, companies that were negatively affected by Obamacare. Okay, so hopefully I've convinced you that synonyms is something that's very interesting, but if you think about it a little bit longer, it's also something that's not as simple as it might sound on the first try. So it's not just a simple database of a few entries, but there's a vast sea of different terms that are slang, that are industry specific, that are acronyms, like UAV, for example, unmanned aerial vehicle, S&P by itself for Standard & Poor, NYSE, clean tech, CFO. So there are various terms out there that you would have to think about how to actually expand. And many of these terms are new. There are acronyms that might change over time, map to multiple things. So this is really not an obvious problem. So how do you approach this? You're a machine learning engineer, you're now coming into this, you want to build a search bar, and you know that part of your pipeline will have to invariably be a synonym expansion. Okay, the most obvious thing, let's say, great, there are dictionaries out there, right? We can go to a dictionary, look up cat, we'll get some information about it, we'll even get a nice little description, and if it's a big dictionary, it will probably also have some synonyms listed for you, right? Feline, tom, kitten, mouser, many that I've never even heard of. And there's the coding equivalent of that, right? So let's take, for example, WordNet. WordNet is effectively an open source dictionary with some meta information on search terms. We can look for synonyms of cat, and what it'll return us various synsets, so different things that this could refer to, and then within those, a little bit of extra explanation. So for cat, you can already see that this maps onto some not so obvious things. Cat, okay, that's great, that's the animal. Cat, also the computerized tomography, that's also great, very different, but also great. And then a few other terms that don't particularly make much sense, but I suppose are also a valid expansion to this. But very quickly, if you try this with other things, right, you type in, for example, UAV, it's never heard of this. This is industry slang. This is potentially a newer term that came out way after this was actually built. So very quickly, this starts to fail. So taking a dictionary will have many problems overall. You'll have potentially no domain specificity unless you made that dictionary very specifically for what you're interested in, paid a lot of money. Data is often, if not always, out of date or old. If you buy it from another company, if you use an open source implementation, it'll always be something that's years and years old. And also the metadata is usually very limited because dictionaries will come with some additional information of maybe noun, verb, or the fact that something is, maps onto two different nouns, but it won't really come with a lot of extra information that will help you to do anything clever beyond that. Okay, so what do? We're a machine learning engineer, right? So let's try to come up with a clever solution. We know that there's a ton of unstructured data out there, right? We know that every day there are thousands of news articles posted everywhere. People post things on Twitter, on social media. We know that there's, in principle, enough information out there to figure out what the right synonyms should be. And the tool of choice, of course, word embeddings. We know, awesome, we have this tool, word embeddings, that we can use to figure out what are words that appear in similar contexts. I won't go into details how you can actually get to word embeddings. I assume most of you are probably familiar with it. Just as as a quick highlight, the idea is the following. Imagine you have a few sentences about Apple. Today, Apple released an iPhone cover. Apple shares surged after the CEO speech. Samsung and Apple are fierce competitors. So even if you don't know any machine learning, from these sentences, you can figure out roughly what Apple is, or at least in what space Apple belongs. You know that Apple and iPhone are potentially something similar, Apple and CEO is something that's often mentioned together, and Samsung and Apple is something that's often mentioned together. So as long as from this you figure out a way to turn your words into numbers or vectors, you can potentially do interesting math after that. So this is exactly our task. So we will try to use all of the surrounding words, released, iPhone cover, surges, surged, CEO, Apple, to effectively turn Apple into a vector so that then we can do interesting things like, for example, similarity search. And this is what effectively we're interested in finding synonyms. And this is sort of as a cute image if we actually do this on a news corpus because we're lucky, we're a big firm, we're Kensho, so we have a nice news corpus that we can immediately throw this on. So this is something cute that you'll then see that actually Julia here made that I really like. This is already kind of a cool pre-processing, right? So this was already a step where somebody figured out roughly what are companies or products. And then after this embedding step of analyzing all this news, you can figure out which of these actually belong together. And you'll sort of see that different companies will sort of cluster together if they're similar. And if you look very closely, you can actually see that some companies next to each other will actually be the same company. So for example, Sony will be right next to Sony Corporation. And this is exactly the kind of thing that we're currently looking for. So maybe that's a good idea. So let's try this out. We train a model, and now we use this nicely implemented function most similar and see what the output is. And the most similar word to Apple is Apple Inc. Awesome, this is exactly what we wanted. It's a synonym for Apple, the company. So does it mean we're actually successful? Let's do a few more tests. So first of all, let's look at some more of the output. So not just the best output here, but a longer list of it. So it's interesting. If you look at it, you can clearly tell that this embedding makes sense, right? Everything that comes back is something that's in some way or other related to Apple. You get Google, Microsoft, iPhone, Tim Cook, Cupertino. But again, the problem here is that you don't really get what you got in your first result, right? You get something that's similar. You don't get something that's the same as the first result. Let's try some other examples. CFO. You get non-executive, Marva Ellison, Brian Cornell, co-CEO. So none of these is the synonym that you're looking for. So what does this mean? This is actually, so I actually kind of like this example because it's very cute. It really sort of, it shows you individual people that are probably CFOs. So it sort of learned that this co-occurs very often with the term CFO, and that's very nice, but that's not what you're looking for. Like, it's almost the opposite of what you're looking for, right? Similar to if you typed in what's a synonym for president, and then you'll get Barack Obama or something. So this is again not really what you're looking for. But you could argue, let's say, this is potentially noise. Getting people that occur once or twice together with CFO, maybe that's noise. We're not amateurs. We can try to be a little bit clever. We can do some filtering on top. But even if you start to do these things, so for example, let's do the simplest thing. Let's restrict our vocab. Ooh. Let's see if this works before I continue talking. Okay. Aha. Yes. First technical challenge solved. Well, second. Yeah, so you do the first, clever thing that you can do on top of here, which is to restrict your vocabulary. You say, I want to make sure that I don't get any noise, because especially if things don't occur that often, potentially, they might not really be a good synonym. So let's restrict our space. And again, you get something interesting. You get CEO, you get general counsel, chief executive. So you get, again, very related terms, but it's very unclear how they really relate to your input term, right? They're sort of in the vein of exactly what word embeddings does. It's similar to or kind of used in the same context as. So in summary, we try to sort of do like a naive ML solution, but it's not as easy as it would sound. And if we really want to do this from a search perspective, what we really need is high precision, right? We need to make sure I'm fine with missing out on a few synonyms, right? But I really care about getting correct expansion. Like the thing that I give you back should better be correct. If I give you a horrible expansion of a synonym, then who knows what will go wrong in any time later down the pipeline. Okay, so there's another interesting thing. If you type into Wikipedia, this Wikipedia page, you don't have to do it, Matt, thank you. But if you type in wiki/Apple Computer Inc., the following thing will happen. You'll get to the Apple Inc. Wikipedia page, and there'll appear a little message here telling you redirected from Apple Computer Inc. So this is kind of cool, right? So you typed in the old name for Apple Inc., like how it was called when it was originally founded, and somebody in Wikipedia added the information that this is actually, that you actually mean Apple Inc., and that's the company that you're talking about. So that's super cool. So can we just do that? Can we just take all of the URLs in Wikipedia that somehow point to each individual entry and take that to be our synonyms? And yeah, turns out we can. So if you, for example, ask now Wikipedia API, give me all the potential redirects for the page Apple Inc., you'll quickly get a list, and this list is much longer than what I'm showing here, but you'll quickly get a list of various different page titles that Wikipedia will automatically redirect to the company for you. And since this is Wikipedia, we have way more than that. So we don't just get the individual titles of the pages, but you also get various different meta information. So for example, you get page views. And this is a little bit underestimated when you maybe just hear that, okay, great, you get page views, but page views oftentimes is really sort of the essence of the start of good machine learning, because it gives you an importance, a sort of a relevance ranking. And whatever you want to do afterwards, you want to filter out entries that are no longer used. You want to figure out what entries are currently being used versus previously being used. So as soon as you start to have information like that, there's a lot of interesting things that you can start to do behind this pipeline. Okay, so for example, in the case of Apple, we can really use this then to make a nice list of our filtered synonyms, come up with maybe we can even tell the client that Apple Computer was a previous synonym, because we'll see that the page views used to be much higher for that. So we can do sort of cute, clever things and really come up with nice, high precision synonyms for each individual input. Okay, so what are we missing? Is this now? Are we done? Do we have a synonym pipeline? Not really, otherwise I wouldn't really be asking like this. So one problem is that it's titles versus in-text use, right? So it's kind of a cutesy thing that you can use URLs for this, but clearly the URL title that maps on a page is not quite the same as something that's being used in text, right? So for example, Apple Inc. will most of the time in a general news context be referred to as Apple. And Apple itself, right, is already a little bit squishy. It's not so clear. Are you talking about the company? What if it's capitalized? What if it's not capitalized? And that's the other big problem, right? So Apple itself will never appear as a synonym. Even if you type in Apple Inc. and ask for a synonym, you will not get back Apple because Apple will not map onto that page, right? It'll map onto the fruit or onto a page telling you that it's a fruit or a company. So we really need to sort of go a little bit of a step beyond that and figure out, okay, how do we sort of deal with the weirdnesses of URLs? And again, Wikipedia has a sort of a nice solution here. Wikipedia also has interlinks. So within Wikipedia, if people were nice and didn't just write a good article, but they also interlink the different websites, you'll have hyperlinks in the middle of a page, and you can extract those. So you can figure out, for example, in the middle of this is about the S&P 500 or something like this. There'll be full text where Apple Computer will be mentioned, and there'll be a hyperlink that connects you to Apple Inc. So this is great, and this will appear all over Wikipedia. You'll have mentions of Apple Computer, Apple Inc. You'll have apples and pomegranate, apple and tomato peels. So having this, you now very, very easily can list down what are the different ways that Apple Inc. is referred to and what are the different ways that Apple the fruit is referred to. And now all you do is counting. By the way, I was told that usually I get very excited when I give certain slides, so instead of trying to get too excited, I just put the little emoji to simulate the excitement. Yeah, so we know what to do. We can analyze now all of Wikipedia and just count different links within Wikipedia and figure out what different strings are mapping to. So what this will look like for Apple, for example, is, okay, somebody types in Apple, wants synonyms for Apple. Great, we know exactly how often Apple links to the page about Apple Inc. and how often Apple links to the page Apple the fruit. So we can say, okay, with 30% likelihood, you mean Apple the fruit, and with 70% likelihood, you mean Apple the company. Sweet, okay, so we have our first step done. We know what entity the person is likely talking about. And then we have the next step. So we can do our synonym expansion using either our redirects or doing the inverse here by just listing the strings that refer to that particular page. So, but okay, I forgot about this, this is awesome. So there are actually even more things that we can do, right? Because I mentioned that we're in the Wikipedia universe, right? So every page has a lot of metadata associated with it, right? We don't just have page views, we have the actual Wikipedia article, right? So let's say somebody is querying for Apple, and we said we know this sort of nice prior that knowing nothing else, I'm assuming you're 70% likely to mean Apple the company and 30% likely to mean the fruit. But what if the person tells me, I can also give you some context. I work in the financial services industry, or I got the string Apple from this sentence here and gives me the sentence, Apple sells computer software, right? So for example, if you're analyzing text, you may just have this type of context around your word. And this is great. We have the whole Wikipedia page. So we have plenty of context to try to figure out which of these two entities the person is actually talking about using the context. So you can use your favorite metrics of TF-IDF overlap or whatever you may have and figure out that given this context now, the prior of 70-30 will now easily change to the person meaning the company here. Yes?
What if you ask, how does the price of an apple affect Apple stock?
You'll probably get something in between. Yeah, I mean, of course, there are always edge cases, right? But I think it depends very much on how you want to do this. And the idea is that the context is something you have full control over, right? Like the context could be as simple as just pass along the sentence that it appears in, or you do something clever, right? You extract something from that particular user, or you try to, for example, this type of question, you would probably try to analyze, do I even have a response for both of these, right? Like, for example, if you have an actual financial product, you may have absolutely no information about the price of an apple, right? So you would just assume that really refers to that company. But yeah, thanks.
How often do you find some of these contextual sort of rebalancing of the weights is a result of something like plurals, for example? If you're not going to talk about anything apple related, you use apples plural compared to the fruit.
Yeah, that's.
Frequently?
Yeah, of course, that's another very good problem, right? Like this is always sort of a little bit of I don't know, somebody will run into an issue where, for example, he types in the plural and he doesn't get correctly routed, and you'll sort of like, this is annoying, and then you'll add stemming, right, and then it'll strip off all S's, and then you'll run into like 5 other problems. Now this created these other problems. So yeah, I mean, of course, a lot of these things are problems. With Wikipedia, it's nice because a lot of this is actually sort of handled by default. For example, apples will be commonly referring to the fruit, but it will never refer to the company. Yeah. So some of this stuff you get for free. Even misspellings is kind of cool. So if, for example, a company is often commonly misspelled in a different way, but sort of still uniquely meaning that company, there's often a redirect. So it's kind of nice actually that some of the sort of the easy wins you'll basically get just out of the box. Yes?
If that process can be applied location-based, we are in a global economy. And based on your presentation, I just imagine, okay, it's based in the United States.
Mm-hmm.
But if you have customers from India or China or Bangladesh, and they go in looking for Apple, most likely you have to change your weight on your prediction.
Mm-hmm. So, if you're talking about sort of further down the pipeline kind of applications, yes, probably, your model will change, your predictions will change, your training data will change. But for the original mapping, that's really cool where you have Wikipedia, right? Like you don't just know that it maps onto Apple Inc., you know what page ID it maps on. And within Wikipedia, you can easily find out what's that page ID Apple Inc. called in 138 different languages, right? And you can literally, translating the input here would be trivial. It's a lookup in the database if you have the data from Wikipedia.
Find a way to estimate or something that affects the stock price.
Mm-hmm.
Can you link suppliers of Apple Inc.? Can you find a way, okay, a big supplier is reporting that the forecast is not going to meet expectation.
Mm-hmm.
That most likely that particular supplier, the bigger clients, in this case, let's say Apple Inc., can S&P database, do they have that data available for the suppliers, let's say, for every company out there?
I mean, yeah, this is a very separate problem. There are various divisions that deal with these kinds of things. I would say it's very far away from the problem of sort of synonym extraction. But yeah, of course, that's another big area in how you can sort of expand your mapping beyond that.
Because I know analysts, they go that way.
Mm-hmm.
Most likely to estimate if the company is going to meet expectations.
Mm-hmm.
They go visit the suppliers and see, talk to the management. And I'm just wondering if with machine learning, if something can be done on that section.
Yeah, we can try to make the next talk about that. But it's a very interesting problem. I agree. Okay, so putting this all together, we actually now have a nice synonym pipeline, right? So coming back to our original problem, we can nicely figure out Obamacare as the PPACA, but we can also figure out UAV. We have synonyms like drone aircraft, Standard & Poor's for S&P, Chief Financial Officer. And the other thing that is maybe sort of, again, important to kind of remind you, right? So we were really sort of shooting for precision over recall here, right? So there are always things that you might be missing, but the important thing is that you get the things that you do figure out, that you get them right. Okay, so in summary, again, to sort of harp on this fact, right? Practical solution, try to find the right tool for the job, right? Like it's very, you come into this problem and it's sort of very, very easy to sort of go into this pipeline of saying, great, synonyms, I can learn it and I can probably even find some training data and I can sort of come up with a very cute solution and say I'm scouring the web, analyzing everything. When in fact there's actually a much simpler method out there that is well curated and updated by the community. Maybe also just to mention, the point here is also not to say that there isn't an ML approach for this or a completely different solution for a different approach. try to figure out what you're interested in, right? So for example, if you're directly expanding synonyms, showing them to the client, you care a lot about precision. If you're having this as a step in the pipeline where some whatever neural net down the road is gonna figure out what happened after this input, you might be totally fine having a rough expansion to related terms, right? So for example, maybe then our original idea of using word embeddings would be exactly the right way to go, right? So try to figure out what are you gonna use it for and what are your trade-offs. Yeah, so putting this all together, we have our Wikipedia database, and without even having put too much work in it, we have an always up-to-date, crowdsourced, surprisingly domain-specific synonyms database that we don't even need to maintain other than the ingesting and communicating with it. And the other really cool thing, right, for everybody doing ML, this is very nice that this is just starting off point for doing any sorts of other NLP down the road. You don't just have the page ID, you have any sort of other information that Wikipedia, Wikidata will have about all these different entries. So there are various different things that you can try to do afterwards. Okay, so if I lost you, please come back now. This is the second part of the talk where we'll talk about record linking. And this is also what the hands-on workshop afterwards will be about. If you chose to pay attention, I guess now it's too late, but if you wanted to pay attention to one, pay attention to this. Okay, so let's start with a simple example again. So what's a standard sort of, I don't know, I called it data science workflow. But what usually happens? Imagine you're being asked to estimate the impact of a hurricane, and somebody hands you a bunch of data, hands you various different hurricanes over the last decades. You have some data about them. You have the date when it happened. You had the rough location, maybe countries, and you're being asked to figure out what the impact of that was, right? Well, what are your first steps really going to be, right? You're probably going to say, well, I kind of need more data than that. Let me go out to the internet and source some data. So let's say we get city population data. That's probably very important to figure out where was this thing, how big was the real impact. But if you get that data, right, you will have per city, you will have population. It comes from a completely different data set, from a different data provider. There will be no unique identifier. This new data provider will probably not have hurricane names next to the cities. And on the other hand, your hurricane data might have differently formatted city names, maybe only country names. So using this new data is, having that is great, but it really only works if you correctly link it to the location of your original data source. Similarly, you might then say, okay, I have city, but I actually need the country, so let me go somewhere else and get a city to country name map. Then you figure out, well, cities are written in a slightly incorrect way or different way across the two data sets. So you have to start to come up with clever ways on how to interlink these data sets. Or say you find another hurricane data set that is partially overlapping, partially not overlapping. You need to figure out, do I want to join these? Do I want to link these and then sort of mix the rest? So you have to really figure out how to connect all of these different data sets just in order to do your job of the original ask of figuring out what the impact of your hurricane is. So this is a sort of this is something that's probably obvious to all of you, but it's really something that's very important for people in the business, that it's not just about having data, but it's really about having connected data, having context around your data, and having data that talks to each other correctly if you want people to be able to do their jobs. So, and this is also, like speaking in industries, it's also interesting how often you actually stumble across this, like whether it's people acquiring new data sources, people just doing inference. It's a surprisingly ubiquitous problem that people are linking data sets everywhere across the industry. Okay, but let's be a little bit specific. So I said I was going to talk about problems at Kensho and S&P. So let's start with S&P data. So S&P has a lot of data, and among other things, they have a giant list of companies. So this is, for example, so it's probably hard to read, but this is S&P data about Apple Incorporated. So they'll have various different data about it, where it was incorporated, what are some of the key executives, what's the street address, what's the temporary second street address. So like a lot of different information about this company. And there'll be many of them. There'll be, let's say 10 million companies. So they'll have a huge data set of various different companies all across the world. But imagine now that they talk to some of their customers. Customers can be from anywhere. They can be in, sitting right here in Harvard Square, or they can be at the other end of the world. So they'll call up S&P and say, your database is great and I use it every day. But actually, recently, I've been interested in startups in Europe. And it seems like you actually don't really have that much coverage in startup in Europe. So what does S&P do? Do we hire people to literally scan the web or news to figure out what startups there are out there just to create new entries in the database? Okay, I guess you could do that, but it's not super scalable, and eventually it's going to cost too much money. And especially, other people have already done that, right? Why not just go out there, figure out which company has that type of data, and buy the data? So for example, Crunchbase is a company that's very heavily focused on the startup scene, and among other things, they also sell their data. So this is great news. We can walk in and without too high of a price, we can buy a copy of Crunchbase data and put it into our database. But of course, what we need to do is linking, because this new data source is not really going to help us at all unless we figure out what we're dealing with and which of these companies we have. And there are really two things that we care about. So one will be finding out which companies we already have in our database, right? So they'll be, for example, Ample Inc., Amazon.com. Like, these are huge companies. Hopefully, both sources will have these companies. So we can quickly figure out, great, we have these links. And we literally can just now port over whatever new metadata we have in the new source. So let's say, I don't know, Crunchbase reports on who is leading the funding rounds and who is transcribing that event. Something that S&P before was not saving, something that Crunchbase is. Awesome, now we have these companies linked and we can offer that as a new data source for clients. There's also the sort of the opposite of this, where certain companies will exist within S&P data, and certain other companies will exist only in the Crunchbase data, right? And this is also good, because that's exactly what we originally set out to doing, right? Having companies that are not in our source is great. As long as we can figure that out, we can just mix them in and bundle them up, and we'll have a larger data source, and people will be happy that we now also cover startups. The two things that maybe I want to point out, right, is that already from very quickly thinking about it, this is not a completely obvious process, right? So for example, in the link here, you have Amazon.com, which is the technically correct company name, and Amazon, which is the much more sort of human-friendly name that people usually refer to it. Now with Amazon, that's pretty obvious, because everybody knows that there is one Amazon, and if there was another one, they would probably get sued. But there are a lot of other companies where it's not as clear-cut, right? And there are different countries where people have very similar company names, or at least partially overlapping company names. For example, even already here, Laser Ships and Laser Barrels. So of course, when you read that as a human, it's a different company, but at least they have some sort of commonality. But let's be a little bit more specific here and come up with an example. So let's say in our database, we have the entry Kensho Technologies. And now within our other data set, we find the entry Kensho Technologies LLC. Being a domain expert, LLC, okay, that's a suffix. I mean, it has a meaning, but maybe it was sort of stripped off and left out in one of the data sets. So probably this is the same Kensho Technologies that you're talking about, so we can make a link here. But then you figure out, whoa, I didn't realize there's actually a Kensho Tech Incorporated and a Kensho Inc. So now you're going to say, well, now actually looking at this, LLC, I mean, it kind of actually does mean something, while incorporated is much more of a suffix that's less important. So it's actually more likely that here incorporated was just left out on the left side, and tech is just an abbreviation for technologies. So I would actually rather here link Kensho Technologies with Kensho Tech Incorporated, and assume that Kensho Technologies LLC is a parent company, a sister company, a former name, or a duplicate entry. So you'll suddenly change your opinion on what your link should be. Now you look at some of the metadata. You figure out Kensho Technologies is at Harvard Square, and the other three companies are in Delaware, New Orleans, and Brattle Street. If you're a clever machine learning engineer like we are, you figure out Harvard Square and Brattle Street is basically on top of each other. So actually we were correct in the first place. So Kensho Technologies LLC is probably the right thing, because the other ones are in completely different areas of the world. But now you get even more metadata. You figure out that this was founded in 2013. So was Kensho Tech Incorporated, while the other ones were founded later, and missing value, of course, because it's machine learning. And now, again, you're going to change your opinion, right? You're going to say, oh, okay, well, so if it was really founded at the same time, Kensho Tech Incorporated is really the same as Kensho Technologies. And Kensho Technologies LLC was founded 3 years later, so it's probably either a name change or a spin-off company or something that's related, but not the same. Yeah, and with this, you have no idea. You're right, okay, does this even belong to any of them? Does this have any relation, or is this just an entry that was somehow incorrectly created, or what should we do with that to begin with? So overall, this is not only a difficult problem, but it's also a very domain-specific problem, depending on what data sets you're dealing with. Are you dealing with a crowdsourced Wikipedia data set? Are you dealing with an official Russell 3000 list? Are you dealing with tickers? So depending on what data sets you're linking, the rules of the game might be quite different. And the way that you end up making these linking decisions like we just saw, it's very sort of many small pieces of evidence, right? Like you'll figure out, oh, okay, they have the same URL, that's a pretty good indication, unless you see, oh wait, there are like 3 other companies that have the same URL, so probably I should rather look at the country where it's being, where it's incorporated in. So there are a lot of these sort of small decisions that will give you slight indications for something being a link or for something not being a link. And this global dataset knowledge is also something that's very interesting and not to be underestimated, right? Exactly like we saw before, it's not really enough to see 2 examples. You need to actually find not just are these 2 examples similar, you need to figure out are these the most similar, or is there maybe another one within your database that's actually the correct link. So overall, this is a task that sort of comes with a lot of problems. So let's see how we can approach this. But we don't despair because we're machine learning engineers. So especially many small pieces of evidence that sort of screams machine learning to you, right? You say like, oh, this is amazing. Like people have done this by hand for the longest time, and all these things that ink and incorporated is the same. That URL overlap is a high likelihood of them being the same company. These are all things that I should be able to learn. And yeah, so we say, great, okay, so what's our plan? So we just make features. Let's make features for things that we believe make companies similar. So we look at the names, we see how are these names different, come up with your favorite string distance metrics, TF-IDF overlap, whatever you may have you. You can look at, are those similar countries? Are they close to each other? You can come up with whatever clever features you think you can come up with. And then as long as you get some training data that was annotated and you have a nice machine learning algorithm, you're good to go. And this is a problem that you know how to work with. So is that what we have? Is it as simple as that? We have a linking problem, we know how to make features, we know that as long as we have training data, we can solve this problem. And again, it's of course not. So what's the other big problem? It's a scale problem. So think about the following. You have 10 million samples. How do you link those? Okay, so if you were to do this by hand, you would do one by one. You would start with the first example, 10 million. How does that work into my other data set? You would effectively have to do a search, right? So you would have to somehow find, okay, for this term, let me type it in. Okay, there are 10 that are similar. These 2 are very similar. So you start to do this iterative process where for every entry, you really have to look over the whole other data set to try to figure out which one is the most likely to map. And if you, now let's think, okay, how do we do this with a computer? Okay, but it should be easy, right? You just look at all possible combinations of comparisons. But very quickly, this becomes completely intractable, right? So you have 10 million entries on the one side, you have 500,000 entries on the other side. You quickly get to something like, I don't know, 5 trillion potential pairs, something that no matter what implementation we choose, will be completely intractable to just brute force through with our machine learning algorithm. So we need to be a little bit more clever than this. And people have done this for a long time. It's become often famous in the image detection community. What do you do if you have too much data throughput and you need to be fast and efficient at making decisions? Well, the clever thing to realize is that you say, well, actually, if you think about it, this is sort of a weird thing, right? Because yes, technically you have to compare every entry to every other entry. But it's kind of silly, right? Because many entries are completely different from each other, right? Like if 2 names don't even share, I don't know, a letter together, what are the chances that's really the same company, right? So you quickly come to the realization that you say, okay, so how about I sort of divide this a little bit up, this problem. I really make one very fast model where I really care about, let me just get the really easy cases right. So you get a very, very high recall sort of filter model, right? So you crunch through all the different combinations and come up with, okay, I'm not great at this, but I'm saying that these 2 million pairs are probably worth it. And then you have a second model that is much better, much more accurate, much slower, that then goes through it and does the actual proper figuring out whether companies are a link. Cool, so how do we do this? So let's try to build a fast model. The main important thing to realize here is making exact string comparisons is very fast. So for example, figuring out does Apple Inc. occur in these 1 million strings is incredibly fast. You build a hash map out of your 1 million strings, and you have constant lookup on whether your entry exists within that hash map. Sweet. And you can do that within Python very easily. You can create a pool of 10 million strings. So I just call set on a list of 10 million strings that are numbers, and then I time how long it takes to check for 500,000 strings, whether they're in that pool of 10 million strings. So this is what I just told you before, that's impossible to do in any reasonable time. You can do in less than a second, right? Because you can use this fact that an exact lookup is much easier to do than this sort of rough, fuzzy comparison. Okay, but the downside is it's only an exact match, right? So, okay, cool, we can do this for companies that are exact matches, but it's kind of stupid because most companies, like I showed you before, are probably not going to be exact matches. At the very least, there are going to be small differences in how they're written. So how do we do this? So let's try to sort of combine the advantages of the exact lookup with a little bit of this fuzziness that we want to actually get some of the less trivial cases as well. Because like I said, we want high recall, right? We really want to make sure that in this first stage fast model, we don't already kick out some potential pairs that then later down the road, no matter how smart we are with our machine learning, we have no chance of capturing. So we really need to make sure that this first model is not only fast, but also really high recall and really keeps all the pairs that are potentially a link. So how do we do this? We make many exact comparisons. So for example, Apple Inc., we not just store as Apple Inc. the string, but we figure out, okay, how about we remove the dot at the end of Inc., Apple Inc. How about we strip the ink altogether, making it Apple? How about we lowercase the thing and strip the ink, making it Apple lowercase? So suddenly we have multiple different representations of this, all of which we can now do an exact match of whether this occurs within our pool of sets. So we're still in the realm of doing basically exact matching, but we're much more clever in how we define exact, right? We can maybe even take certain aliases for Apple Inc. Maybe we're already using our synonym set. We figure out, oh, actually this is sometimes Apple Computers Inc. So maybe we should also check whether Apple Computers Inc. is in there. So this is the main idea. We have a very fast model that we can, by using these different hash functions, we can basically figure out very quickly if our input string is potentially in the other data set. There will obviously be a lot of incorrect results as well, but at least we hope that we capture all of our correct ones. And also just to mention, you're of course not limited to doing this with strings or with aliases for that company. You can also of course do that on any other attribute, right? So for example, if you know excuse me, if you know that zip code, is, for example, an interesting thing. Zip codes here are relatively large. Zip codes in other areas are much smaller. It's a very good notion of exact physical location. So by doing just zip code overlap, you already have a pretty good chance that two companies might be the same if there are only, I don't know, five companies per zip code. So there are several different other attributes that you can also use for your exact lookup to define potential pairs within your data sets. So let's see an example. Does it make sense, anybody? I want to make sure that I pause here a little bit. I'm going to give a little bit of an example on how to do this now in practice with your data sets, but I want to make sure that this is excellent. Okay, so we have two amazing companies that sadly don't really exist. It's Kitty Cat and Friends Inc. And it's the Kitty Cat and Friends Corp. Now, again, looking at this, it's pretty obvious that these are the same company. Assuming that there are not two people that would name their company that. But it's still spelled very differently. So what do? We apply our different hashing functions. So we figure out, okay, in fact, for a string, that's basically tokenizing, right? So let's say, okay, we know that this has several attributes. We know that Kitty appears here. We know that Friends Inc. appears here. And we know that Kitty Cat, for example, appears here because we defined the rule that we strip all the dashes and eliminate spaces and then take the first, I can't count, 2, 4, 8 characters. So we know that this string now basically hashes to these 3 inputs. And we can do the same on the other side. We know that the Kitty Cat and Friends Corp hashes to Kitty Cat, Cat and Friends Corp. And now doing these exact comparisons, right, we can nicely see, oh, okay, I mean, they're written quite differently, but at least, by doing these these clever different techniques, we found that at least in Kitty Cat they're overlapping, so we're going to keep them around as a potential comparison for the next round. So you do this for all strings on all sides, and then you look at each of the individual attributes. So in this case, for example, imagine you did this for all of your 10 million S&P companies, and you did this for your 500,000 Crunchbase companies, and then you figure out, oh, there's the attribute Kitty Cat that I have, and there are 2 S&P companies within that and 3 Crunchbase companies that share this attribute. So all you now need to do is say, okay, great, I multiply these, take the different permutations. So I now do 6 comparisons where each S&P company I compare to all 3 possible Crunchbase companies. So I'm done. So for these 5 companies, I now need to only make 6 comparisons instead of millions of comparisons to all the other potential companies that this overlaps with. And this is exactly what we set out to do with our fast model that we do as a pre-model. Okay, cool. So second model. We're now down to a much more tractable list. We're not talking trillions anymore. We're now talking maybe 1 million or something on that order. So it's something that we're much more able to do with normal machine learning, feature generation, exactly the tools that we know how to use well. So as we discussed, you take your features, you take your favorite binary classifier. This is now boiled down to a classification problem. Are these 2 inputs the same? Given all the strings, given all the names, given all the metadata, what's your output? I mentioned the different estimators here kind of purposefully, just because in practice, in routine pipelines, all of these 3 estimators are constantly being used. So it's one of these things where it's kind of interesting. I remember when I first started working on this, I was kind of like, well, how could it possibly be that one company will be using logistic regression and then the other company will be like, oh, we're smarter, we're going to use gradient boosted trees. But it really depends on the training data. It depends on the data that you work with. It depends on how sure you want to be not to screw anything up. So really actively, multiple different estimators can be used here. And now all that we needed to do is say, okay, cool, so we can make all of our features, we know what estimator to use, so now all we need to do is get training data, right? So how do we get training data? The first most obvious thing would be, okay, let's draw some of the samples randomly and let's ask people to annotate what are the correct matches for these. I want to mention already now that sort of one of the common problems here is to some extent bias, because what you often give people is you give people pairs, right? Like you'll give people 2 companies and ask them, are these 2 companies a match or not? And this is how most annotation frameworks will easily work. You'll just look at it, okay, this is the same company, this is not the same company. And like we saw before already, this is very dangerous because often just from a pair, you can't really figure out if 2 companies are a pair or if there's potentially a better match. Or how did you even select these companies in the first place, right? Oftentimes, let's say you're S&P and you're now saying, okay, great, let's annotate some samples by hand. Well, which ones are we going to annotate? Well, let's start with the Russell 3000, right? So then everybody has annotated the Russell 3000. Great, we have training data, but this has now introduced crazy bias into this system, right? Because we only now know pairs that are huge companies, right? We know how to link a company that's Amazon or Apple, but if you think about it, those are the easiest ones to link, right? Because they come with a ton of meta information, they have URLs, they have locations, they have, you'll probably know something about their leadership team. So those are the really easy ones. So you need to make sure that the training data that you have has the least amount of bias it can have, or at least that you're aware of how this was created. There's also the interesting question of negative samples, right? So is something a sample or not? The interesting thing is here, since there's a sort of this dimensionality explosion here, you can randomly pick a pair of 2 companies and you can be pretty sure that they're not a pair. So finding 2 companies that are not a link is actually surprisingly easy, right? So you can negatively sample pretty much as many examples as you want. However, that's not really going to teach your algorithm a lot, right? That 2 different strings that don't share any common attribute, that those are not the same, is probably not going to help your algorithm that much. So also here you have to be careful in what kind of samples you actually want to sample. So you sort of end up coming almost with a sort of an adversarial approach to this, saying, okay, I really want companies that have similar strings, but are not actually the same company, right? So also that is not a trivial example. Another interesting thing is here that this is also one of the nice areas within machine learning where active learning is actually used a lot. And I'll come to that in a second, but the nice thing here is really that you can sort of already start out with a solution that is to some quality, and then iterate from there and just make it better and better. And actually, let me try to explain this in a little bit more detail for people that are maybe not familiar with active learning. The idea of active learning is that you will have an algorithm that trains on the training data, makes a prediction, and then from that prediction output, that will inform your choice of what samples to have next labeled. A human will annotate those examples. They're going to go in a circle. It'll get retrained. Your algorithm will make better predictions, hopefully. And then again, the human will annotate. So it will be this active loop where your algorithms will be retrained, and your experts will label only the examples that you choose are best to label. So there are various different strategies that you can do here, but the basic idea of active learning is usually that you say, well, you're greedy. Do you really want a person to keep annotating the same problems? No, I mean, I already know that Inc. and Incorporated is the same thing, right? I don't want to keep giving my industry expert the same silly, obvious example to label, right? So instead, I want to make sure that I give them hard examples. I want to, have them label companies that are in some country where we have almost no information, where there are weird Unicode symbols in the names. Like, that's the kind of information I want to get out, right? So what I do is I look at the histogram output of my estimator. So you'll see here that there are big peaks around 0. And around 1. I mean, and so your algorithm is nicely doing what it should. It classifies a lot of the links as not being links and a lot of the links as being links. But then there's this huge sort of chunk around 0.5 where the algorithm doesn't really know what to do. So what you can do is you can pick your annotation examples out of this bucket in the middle and have those be annotated next, because those are hopefully the hard examples that your algorithm will learn from a lot. Usually this is done in a sort of a slightly heuristic scheduled approach, because the problem, of course, is if you do this procedure, you're again introducing bias, right? So you're basically saying, okay, I want to only have the things that my algorithm is already not sure about labeled, but what if your algorithm is wrong, right? Like, what if your algorithm to start out with already misclassified a bunch of stuff from 0 to 1? Then by only picking the examples that are at the decision boundary, around 50%, the algorithm will just keep making those mistakes and will never end up correcting the things that are maybe very obvious mistakes. So the way that this is usually done in practice is that you come up with some sort of schedule where you say, let me choose some examples randomly, let me choose some examples very greedily to get more information, and then sort of combine these to get both a robust and an efficient estimator. Okay, so putting this all together, what does our linking pipeline look like? Oh, sorry, please.
When you say explore versus exploit, that's what you meant by random sampling versus...
Yes, yeah. Yeah, so putting this together, our linking pipeline will now look the following, right? There's a lot of pre-processing. We can either sweep that under the rug or talk for 10 hours about this. As often, this is of course one of the biggest tasks. But then we have our first stage model, fast, filters down all of our data to a tractable comparison. We usually end up starting with some sort of seed training data. I'm sort of mentioning this here a little bit specifically because you can either say, okay, I don't have any training data, so let me just pick random examples out of there. Or you can maybe be a little bit clever there. That's why I sort of called it seed train data, because sometimes there are parts that are maybe already linked, or maybe there are parts that have a unique identifier. Maybe there are tickers that are direct overlaps. So you can say, okay, this is maybe not great training data, because again, it's biased to large companies, but having ticker overlap in these two data sets at least gives me some training data on which companies should be the same. Then you go to your two-stage model, you figure out are those really duplicates or not, keep sampling, keep expert labeling, you do this as often as you want in your active learning loop, and then you come out with your results in the end on whether companies are links or whether companies are not links. Okay, another thing that's kind of interesting though is, let's say we have now built this whole pipeline. We know for every link that there could possibly be there what the probability is for those to be a link. So we'll have Apple Inc., Amazon Inc. that we already knew from the very get-go, super high likelihood to link, 97%, 98%, awesome, okay, nice, those were easy. These other two companies, again, we know that there are no links, and with a very small, they're basically the highest likelihood match for them would be below, let's say, 25%. So again, this is exactly what we wanted. We know these are very likely unique entries within those data sets, so we can just add them together. But now there's a lot of bulk sort of remaining parts in between, right? So what do we do with everything that's not obviously a link or not a link? And so let's say, for example, what if I tell you that United Sales is 43% likelihood to link to Sales United Inc. and 51% likelihood to United Sales. This tells you almost nothing. And this is important to realize, right? Because in the end, if you're developing this for a customer, you will end up coming up to them and being like, okay, cool, yeah, we did this great machine learning solution. You have all of your links, you have all of your ejections, and then you have this huge pile in the middle where we have no idea what to do with. And the interesting thing here to realize is that that's not necessarily a bad thing, right? So depending on your data set, for example, this could be as simple as United Sales is linked to both of them. Maybe both of these are actually an incorrect duplicate of each other. Maybe it's a parent company and a sibling company, and we just don't have this granularity in our other data sets. So linking this one company to these two other companies is completely correct, right? So this is where a lot of business logic comes in, where you need to figure out what are your requirements, right? Another way of dealing with these could be, for example, to say, well, we paid money to get new companies. We don't need to get all new companies from this other data set. So why don't we just call it quits, throw out the middle, and just keep the bottom at the top? Great. So it really depends on what your business logic down the road is, how you want to actually then end up combining the outputs of this algorithm into a usable project of these combined data sets. Okay, so to quickly summarize, again, make sure you choose the right tool for the job. In this case, it ended up being a combination of some clever engineering, standard Kaggle machine learning, and even some cute active learning that actually really helps your product. Another reason why this is interesting is because, like I said, this is a really ubiquitous problem. In most companies, this will be a problem that keeps on coming up, and oftentimes it'll be solved either through human annotation, or things will be partially linked or incorrectly linked, or done for once but then sort of left. So this is a problem that keeps reoccurring. So oftentimes this lends itself very well to seeing what other similar jobs have been done there, right? And if you think about it, for example, comparing companies from different sources, or even comparing strings of company names, right, is something that you can learn a lot from, right? If I've linked another data set, 3 months ago, where I've learned what different company suffixes mean and which countries or large countries have many duplicate companies, that knowledge I really want to bring over to my new linking task, right? So it also lends itself very well to using your previous linking data and do transfer learning or any sorts of cute games that you want to play on top of this to really utilize all the previous work that was already done before. The other thing to do, like I mentioned before, make sure you know the quality requirements. In many linking tasks, people will care less about the exact quality. Maybe they want a quick, rough link, and if you get some false positives, they'll be perfectly fine with it. Maybe they care really about false negatives. There's always very different requirements about all these tasks, so make sure you know what you want before you spend too much time on actually investing into getting these pipelines fast or accurate. Cool, so with that, I'll conclude. I hope I sort of managed to talk about these two topics that I actually like quite a lot in a sort of a very direct way, as in like how we were thinking about it at the time, and how we sort of try to iterate from one solution to the next, and how we ended up really choosing different, completely different approaches. And while you might have your, I don't know, tower running on the side, but then at the same time, writing some code in your Python shell that somebody could have written, I don't know, 30 years ago, right? And I think that's really something that's important to realize. Also, of course, we are a startup, so we're always looking for good people. So if you love machine learning, talk to us, send us an email. We'll be around wearing these blue hoodies. I'll get to that more in a second. Also, we have this beautiful new AI lab space. We love to host events here. If you want to talk about something, if you have friends that want to talk about something, this is the place to go. We host regular events. Check back there, sign up. We're hopefully hosting cool stuff in the future as well.